Now we're going to talk about the inverse of a matrix. So if we have an n by n matrix, notice that has to be a square matrix. It's going to be invertible if there is some matrix B so that A times B is equal to B times A, which is going to give us the identity. So notice that multiplication can be done in any order, and then we'll get the identity for an n by n matrix. So a couple of little things here. First, you got to have a square matrix. The only way it's going to be invertible, or possibly invertible, is if you have a square matrix. If it's invertible, we say it's non-singular. Singular matrices means that there's no inverse. But if it's non-singular, then that means it does have an inverse. Okay, also, there's some commutativity going on here with that multiplication. A times B and is equal to B times A, which is always going to give you the identity matrix. So if we find a matrix B where that happens, then we would say B is the inverse. And we can write the inverse this way with A to the -1 notation. Now, what's kind of cool is that inverses are unique. If there's an inverse, there is only one inverse. So let's go through and prove that. And we're going to prove this. Here's what we're going to do. We're going to let B and C be inverses. Now, our goal is to trying to do two things at once. All right, let's try again. So our goal is to show that an inverse has to be unique. So our approach to this proof is to say, suppose it's not unique. Suppose there are two inverses. Then what we're going to show is that those two actually have to be equal to each other, which means that it is unique. So we're going to say, let's let B and C both be inverses of A. Now, A, B, and C have to be square matrices in order for this to work, because the only thing that can have an inverse is a square matrix. So we're going to let B and C be inverses of A. So by definition, if that happens, then when we take A and multiply by B, which is one of the inverses, we can do that in any order, and we're going to get the identity for that n by n matrix. I'm going to call it I sub n. But if we do the same thing with C, A times C, because C is an inverse, then we have to get the identity also, and we should be able to multiply that in any order and get the identity. So we know that A times B is equal to the identity. Now, let's multiply, because we've already established that, let's multiply by C on the left-hand side. As long as you do the same thing to both sides of the equation, it's a legal move in math. And we already know this multiplication is going to be defined because everything's an n by n matrix. So if we change that grouping on the left, so we now have CA times B is equal to C times the identity. But C times the identity is really just going to be the C matrix. So on the right we have C, but we said C was an inverse here. And C, the inverse, times A has to be equal to the identity matrix. And the identity times any matrix will be that matrix. So we started out by saying, suppose we have two inverses of matrix A. And we went through and we used the properties of inverses here, in the first two lines. And then we said, well, what if we multiply, if we start with this statement, we multiply by C on the left. And when we do, we end up showing that B is equal to C, which means that we can't have two unique inverses because they have to be equal to each other. Therefore, so we're going to use that abbreviation. There's three little dots that's in a triangular form. Therefore, the inverse of a matrix must be unique. So the inverse of a matrix is always going to be unique. When we find the inverse of a matrix, the way we do it, we take A and we augment it with the identity matrix. And then we're going to do some row reductions and we're going to get the identity on the left. Whatever's on the right will always be the inverse. Now, if you remember back maybe to an algebra class, you may have seen that the inverse for a 2 by 2 matrix had a specific formula. So if we have a 2 by 2 that looks like this, I'm just using A, B, C, D here, then the inverse is going to be 1 over AD minus BC. This is actually called the determinant. And that's the determinant of a 2 by 2. And then this matrix, you can interchange those two entries, then flip the A and D, and you negate the B and C, and that's where that formula comes from. Now, we can go through and we can prove that, but I want to prove it in just a minute. I want to play with this idea first with numbers, and then we'll go through and then we'll prove it using letters. So let's look at an example. Let's look at number 7. Number 7, we have this matrix 2, 0, 0, 3. So if we want to find the inverse, we're going to augment that with the identity for a 2 by 2. And then what we want to do is row reductions to turn this left-hand side into the identity matrix. So our first step is going to be to take row 1 and replace it with 1/2 row 1. And then we're going to go ahead and take row 2 and replace it with 1/3 row 2. This one's going to be a super simple one. So if we do that, that first row will end up being 1, 0, 1/2, 0. The second row is 0, 1, 0, 1/3. So there's that identity we were talking about. This is for a 2 by 2. This will be our inverse matrix. So in this case, our inverse will be equal to 1/2, 0, 0, 1/3. This one was a nice simple one because we started with a diagonal matrix. Now, if you ever wanted to check, you can always multiply A by its inverse and make sure you get the identity. You should always multiply it both ways just to confirm that it's correct. If we were to do that here, we will end up with the identity in both cases. So this will work out. Your calculator also can find the inverse if we were to type this in. So we're going to go second matrix, edit. This was a 2 by 2. There it is. I'm going to go back to the home screen, hit second quit. Then we're going to go second matrix, math. And I'm going to use that inverse key. And then I want fractions, so I'm going to hit math. and then turn it into fractions and hit enter. So this is a good way to double check it to make sure you've got the correct inverse. If you go to second matrix math, there's lots of things under here, determinant, transpose, and so on. So let's do another one. Let's look at number 9. Number 9, we're looking at 1, 2, 3, 7. We want to find the inverse. So we're going to pair this with the identity. And now we're going to do row reductions. So row 2 is going to be row 2 plus -3 times row 1. Notice row 1 stays the same. So we're going to have 3 plus -3, 7 plus -3 times 2, 0 plus -3 times 1, 1 plus -3 times 0. And then row 1 will be row 1 plus -2 times row 2. So if we do that, we're going to have a 0 here. That's going to give us the identity, so I'm going to use a shortcut there. And then it's going to be 1 plus -2 times -3. 0 plus -2 times 1. So here's our inverse. And like I said, we could always check and verify that with the calculator. We could also verify that A times A inverse equals A inverse times A, which is equal to A. Just kidding, which is equal to I. So we can always verify that that works. Let's do one more. Let's do 16. So we have the matrix 10, 5, -7, -5, 1, 4, 3, 2, -2. This is where you may want to pause the video and try to do row operations here. So this one's probably going to have some fractions in it. I don't think I'm going to avoid them. I think I'm going to just go for it. So row 1, I'm going to replace it with 1/10 row 1. So we're going to have 1, 5 over 10, which is 1/2, -7 over 10, 1 over 10, 0, 0. Everything else stays the same. And I do like to keep this line in there just so I can kind of keep up with what's what. So next step is to zero out everything under here, under that leading 1 in the top left hand corner. So row 2 is going to be row 2 plus 5 row 1. Row 3 is going to be row 3 plus negative 3 times row 1. We're going to have to be very careful. Top row stays the same. Row 2, so negative 5 plus 5 is 0. 1 plus 5 over 2 is 7 over 2. 4 minus 35 over 10 is 1/2. 0 plus 5 over 10 is 1/2. 1 plus 0, 0 plus 0. Row 3 is row 3 plus negative 3 row 1, so we're going to have a 0 there. We're going to have 2 minus 3/2 is 1/2. We're going to have negative 2 plus 21 over 10. One-tenth. We're going to have 0 minus 3 over 10. 0 plus 0. And 1 plus 0. So now we need a 1 here. So let's take row 2 and multiply it by 2 over 7 row 2. And while I'm at it, I'm going to go ahead and get rid of fractions on that bottom row. I don't have to, but I'm going to see if that just makes it a little bit easier. It may make it easier, it may make it worse. We'll see. So if we multiply row 2 by 2 over 7, and I'm multiplying by 10 here. So now we need a 0 here. So then row 3 is going to be row 3 plus negative 5 times row 2. Just double checking everything before we go on. So first 2 rows stay the same. Five minus 5 is 0. 1 minus 5 over 7 is 2 over 7. -3 minus 5/7. -26/7. 0 minus 10/7. 10 minus 0. So now we're going to take row 3 and replace it with 7/2 row 3. Just double checking to make sure we didn't miss anything. All right. So we're going to take row 2 and replace it with row 2. -1/7 row 3. And then row 1 is going to be row 1 plus 7/10 row 3. So I'm going to start with row 1. So 1 plus 7/10 times 0 is 1. 1/2 plus 7/10 times 0 is 1/2. -7/10 plus 7/10 is 0. And then we have 1/10 plus 7/10 times -13. I got -9. And then we have 0 plus 7/10 times -5. -7/2. And then 0 plus 7/10 times 35. (49/2). Row 2 is row 2 plus -1/7 row 3. So 0 plus 0 is 0. 1 plus 0 is 1. 1/7 minus 1/7 is 0. And then we have 1/7 minus 1/7 times -13. It's 2. 2/7 minus 1/7 times -5. That's 1. And then 0 minus 1/7 times 35. is -5. Bottom row stays the same. So now we're going to have row 1 equals row 1 plus -1/2 row 2. And if I do that, that's going to give me the identity here. I'm just going to write I3. So -9 minus 1/2 times 2 is -10. -7/2 minus 1/2 times 1. So that's -8/2, which is -4. And then 49 over 2 plus 5 over 2 is 54 over 2, 27. So this guy is our inverse matrix. Oops, wrong notation. There's our inverse. And we could always double check this. Like we said before, we could plug it in the calculator. We could see what we get. But this will be the inverse for this matrix. And let's do one more. Let's look at 26. So 26 is a diagonal matrix. And diagonal matrices are easy. So row 1, we're good. Row 2 would be 1/2 row 2. Row 3 would be -1/2 row 3. And then row 4 would be 1/3 row 4. So if we were to perform all those operations, we'll end up with the identity for 4x4 on the left. And on the right, that first line stayed the same. The second line, we're going to take 1/2 of it. The third line is a -1/2 of it. And the fourth one is 1/3 of it. So there is our inverse matrix for that one. So that one's super easy. Diagonals are really nice to deal with. And then let's look at 25. So 25 is kind of interesting. It's still a diagonal matrix, but there's a 0 down that main diagonal. So you would probably start, this the same way. You may not notice in the beginning that you would have a 0 down the diagonal. So row 1, you would want to take -1/8 of row 1 to get a 1 in that top left-hand corner. You're good on the second row. The third row doesn't have anything on that left-hand side at all other than 0. And then that fourth row would be -1/5 row 4. So if we do that, here's what we have. Row 2 was good. So then you may say, well, I need to move rows of zeros to the bottom. So you may want to interchange row 3 and row 4. And that's where you're probably going to notice that there's definitely an issue. Because check out what's going to happen. There's no way I can turn this into the identity for a 4x4 because I'm missing a 1 in that third column. So what's going to happen is that this guy is not invertible, which means it's a singular matrix. So this guy just does not have an inverse for that matrix. And sometimes that will happen. You won't have an inverse for a matrix.